In this example, we're going to use this hotel canopy as motivation for another application of the generalized stiffness approach, which is all going to set the stage for the direct stiffness model later on. Right, this happens to be a canopy that was of a historic nature, needed to be renovated, and so then they came back with something that looked like the original cast iron material. Now, for reasons that will become a little bit more apparent later on, we're going to turn that canopy around so that it's hanging over to the right instead of to the left. But the simplistic model of this thing here is that we got this hanger rod here. We do have a beam that comes along in this location. We'll handle the nature of that beam here by the time we're done with the example, but we're going to look at it as though it were a simplistic truss, which is not too far off the mark. Now, the angle of inclination of the hanger rod is 0.8 rise to run, and that gives us an angle here of about 38.66 degrees. It's like 656 or something like that. So the length of the diagonal is really not quite 12.08, it's something like 12.086 or so. Both are made out of steel, even though they might look like they're cast iron. The area for the rod is 3.14 divided by 4, so that's pi divided by 4 square inches, and then the area for this beam right here is 5 square inches, and its length is about 10 feet. Now, because we're looking at stiffness and we're talking about trusses, and that means two-force members, and so the stiffness that we're really going to be interested in is the axial stiffness. I'm going to just look ahead and do a couple of real quick numerical calcs so that some work later on here will be a little bit easier here. So this will be member 1, that will be member 2. So the axial stiffness of member 1 is going to be then EA over L. So 29,000 kips per square inch times our area of 3.14 divided by 4 square inches. So we'll have kips in the numerator, and divide by 12.8 feet. It's usually more convenient to do this in terms of inches, so let's do that as well, and let's do a quick calc on that. 29E3 times 3.14 divided by 4 divided by 12.8 divided by 12, and we get 148.2 kips are required to elongate that rod by 1 inch. It's a lot of force. And yes, indeed, axial members responding in axial mode are quite stiff. So for the second one here, 29,000 again. This time the area is much larger at 5, and the length is a little bit shorter. So of course this will turn out to be quite a bit then larger in stiffness. 29E3 times 5 divided by 120, and we get 1208.3 kips per inch for that axial stiffness. Right, so this is, initially you might wonder, why are we doing all this? Well, this is just motivation to get us into this idea of the generalized stiffness method that will then be useful or helpful to us later in how we go about analyzing the system for any set of loads. Right now, one of the first and most important steps in the stiffness method is identifying the kinematic degrees of freedom. So we look at these two supports, and those are not going to translate. So let's come out here and identify the X and the Y translations as our first 2 degrees of freedom. Now, it is also true to say that we have degrees of freedom over at the supports, so a total of 6. It's just that delta 3 will equal delta 4 will equal delta 5 will equal delta 6 will be 0 in our model, whereas delta 1 will not be 0 generally, and neither will delta 2. So those are our free kinematic degrees of freedom in the system. Total of 6, 4 of them associated with support conditions, 2 of them free. And so that's why you see in this next step here, in thinking about the generalized stiffness approach, in we're going to be a little bit more general than we have in other examples. We're going to allow more than one displacement to be of interest to us in sort of independent kind of fashion. That we're only going to look at two displacement patterns corresponding with these first two that are free. And so the way this works here is that if I'm looking at just one of these, I'm going to let delta 1 equal 1, and I'll let delta 2 be equal to 0. Whereas then the other one, we'll just flip-flop this. What that enables us to do is a different kind of superposition, that the real system then will be a superposition of somehow these two scale together. Now you're usually used to thinking of that in terms of superposing different force results. Here it kind of is, but really we're going to superpose different displacement patterns back up into whatever the original situation might turn out to be. So with this first case associated with degree of freedom 1, what we want to do is we want to extend out the first one in terms of a unit displacement. I'm going to, for the just initial sake of this here, I'm going to let that just be called delta 1. And delta 2 then is identically 0. So this joint has moved out directly. Well, let's give these joints a name. Let's call that A, B, and C. And so down here that would be A, B, and C as well. Right, so that would be the initial displacement pattern, and it means that then, of course, this BC member will have just directly elongated by delta 1, whereas the other member, AB, will also have turned out to elongate, but not exactly by delta 1. Instead, what we want to do is draw a line that's perpendicular, and that we'll get to that relationship here in just a moment about what's going on in that little triangle. But let's move on to the second displacement pattern, what that would look like. There we have delta 1 0, and then delta 2 is a unit value, so that will go straight up. There's your delta 2, and once again then that'll cause AB to deform. And then first order theory, then the bottom member, which will have translated by delta 2 exactly perpendicular, small deformation theory, it won't have in our model elongated, which is kind of weird, I know, because it looks like it would swing right up, but the fact that that's that right triangle there, we're going to later on ignore what happens there. Right, so no, that's a little kind of confusing about how that might all play out. Let's start to dig into this a little bit more. In order for this displacement pattern to occur, we'll have to impose a set of nodal forces. And with these declarations of degrees of freedom up here, like we've got, that's our global coordinate system, then this will be K11, the force at degree of freedom 1 associated with the unit deformation of delta 1 being 1. And then there will be a force necessary in direction 2 caused by that unit displacement. Right? So these stiffness symbols have that very special meaning that they are the force in degree of freedom I associated with that displacement pattern, which is a unit displacement at J and all other displacements 0. That last part is crucial. Right? So that's what these are. KIJs are really forces or moments when we get into beams later on. Right? Likewise, we've got the same kind of thing going on over here. This will be K due to at 2 due to the unit load at 2, and then K at 1 due to the unit load at 2. Right? So now let's look at this in even greater detail. And so for this first one, note that the elongation of BC is going to be exactly equal to delta 1. We can see that directly right from this drawing. Now, this little angle here, even though it doesn't quite look like it, is still alpha. So the elongation of member AB is going to be equal then to, if that's delta 1, then it only elongates a fraction of that. That'd be delta 1 times cosine of alpha. Right. Now we do a free body diagram and we just apply equilibrium to find out what's going on here. Right, so we've got our little point there. We've got K11 shown in the positive direction. We don't know that it will really be positive. And then, though, we are going to use positive elongation, positive tension in the members. And so that means that we would have the force in BC pulling away from the joint and the force in AB pulling away from the joint. Right? And so let's get the little angle in there. There's your angle alpha again. That's 38.66. Okay, well, it seems like a lot of work, and it is. Right? So K11, then by equilibrium here, K11 is going to have to be equal directly to FBC plus then the x component of FAB, which will be FAB times cosine alpha. Right? Well, through our force displacement relationship, which says that FBC is equal to the axial stiffness of BC times the elongation of BC, right? That's just another form of delta equal PL over AE, right? Just rewritten, right? We've got that plus then KAB times delta AB times cosine alpha. Right? Well, we have a numerical value for that, KBC, but I'm going to put in the actual axial stiffness part here so you can see it. I'm going to substitute in for delta BC, that's equal to delta 1, plus then we got KAB, which is EA over L for AB, times the delta AB, which is delta 1, times cosine of alpha, times another cosine of alpha. Right? And so now that is going to be equal to, where's my numbers? KBC, that's this bottom one, that was 1208.3 times delta 1 plus then 148.2 times delta 1 times cosine squared alpha, which is 38.66, and we end up with then 1208.338 plus 148.2 times then the cosine squared, and we get 1298.6, or about 1299 kips per inch, times delta 1 would be your symbolic K11. So really what you've got is your K11 is really this value right there. Okay, that's just K11. Now we got to get K21, which we're going to do by then summing forces. This was summing forces in the X. Now we sum forces in the Y. Right? Now this one, come back over to here. We get K21, then is going to be equal to the opposite of FAB times sine alpha. Right? So there's a negative sign in there, and that's really important. We're showing everything in its positive coordinate system, and so minus FAB. FAB is the same thing as KAB times delta AB, and KAB was 148.2 times delta AB, but delta AB is cosine alpha, so we're going to get a cosine alpha, sine alpha times delta 1, And so when we do that, 148.2 times the cosine of that times the sine of that, and we get then minus 72.3 kips per inch delta 1. And there again, your K21, because remember delta 1 was actually equal to 1 here in this displacement pattern, so that's why K21 is what that portion is that's left over, right? So that's the first two, and then we got to do the same thing for K12 and K22, right? Well, all right, so let's go look at that one a little bit more carefully. Notice that in this case, again, first order theory, then when the member end only moves perpendicular to its long axis, it doesn't actually elongate in a first order theory model. Okay, so delta BC is going to be 0 for the second displacement pattern. Delta AB, right, now remember, positive is elongation, and when delta 2 is up a unit, that means that the member actually shortens. So we have a minus delta 2, and then notice here's our angle alpha, so that makes this angle alpha up here, because there's your right triangle again. And so we're opposite of that one, so that means delta 2 times sine of alpha is what the displacement compatibility or relationship is. Right, now we do the same thing that we were working on before, almost. Again, it's a little weird at first how you make this all work out. Show the joint forces in the way that would be positive. So there's your K22 and K12. Then we already know that the AB force is 0. Need to show it in tension, and we need to show then as well the positive sign convention, then our force for member AB in tension. Even if we don't think that's the way it's physically going to end up, this is now theoretical work here. Right? So we're going to sum forces, let's sum forces in the Y this time, and you get then K22 is going to be equal to minus FAB times, then we want the opposite part, the vertical part, so sine of alpha, and then FAB is this going to be KAB times delta AB. KAB is the 148.2 kips per inch times our delta AB, but our delta AB was a minus delta 2 times sine alpha, and then we got to hit it by another sine of alpha. And here I'm just going to show it directly, get that delta 2, it's equal to 1 here. And so now that's why you're going to end up with then that K22 is 148.2 times there's our angle, and needed to get that back. Alright, so we need sine squared of that times our 148.2, and you get then, notice the minus times the minus, 57.8 kips per inch for our value of K22. For K11, we will sum forces in the X, and we'll see again, because AB doesn't elongate, it's 0, so we only have K1, sorry, not K11, but K12 is going to be equal to the opposite of FAB times cosine alpha, and that will be then minus, oops, sorry, there's not a minus there. There's not a minus there, but there will show up one, because we'll have KAB times delta AB, and that's equal to a minus delta 2 times sine alpha, and then we have the cosine alpha, and again delta 2 is equal to 1, and so and I need the stiffness value in here, 148.2, and so that'll better be what we just had before, where we had 148.2 times the sine times the cosine. Yep, 72.2, or minus, really, so minus 72.3 kips per inch for K12, and those are our 4 stiffness coefficients, and they're all going to be associated here with the stiffness of this system. Right? In the next little part, we're going to put that all together now. Okay, because again, we can look at then our system as being our actual real system can be thought of then in the following kind of way. Here's our applied nodal forces, and instead of separating this out into F1, F2 and doing those individually, what we're actually going to do is focus on, as a result of these 2 sets of nodal forces, then we end up with a displacement at 1 and maybe a displacement then in the 2 direction. And we're going to then look at this as the superposition of the pattern, the forces necessary to create this pattern. That delta 1 is all isolated to this case. It equals whatever it's supposed to equal. And then this one is where delta 2 equals whatever it's supposed to, and delta 1 equals 0. And that will require a set of forces here to make that happen. And the set of forces that combine here have to end up equaling F2 and F1. So this would be the force at 2 caused by the unit load at 1 times the actual displacement at 1. This would be K11 times delta 1. This one would be K22 times delta 2, and that would be K12 times delta 1. Oh, sorry, delta 2. And so now note the equilibrium we end up with is that F2 equals K21 times delta 1 plus K22 times delta 2, and F1 equals then K11 delta 1 plus K12 delta 2. And although I got these in the reverse order of the way we usually write them, what that looks like in matrix form is the following. That second equation is K11 times delta 1 plus K12 times delta 2, and then the other one would be like this. Yes, it's symmetric. K12 will equal K21. That's a critical thing, but this is our stiffness model here. And then you might ask, well, now wait a minute, you said the beam might not actually be a truss member. It could have some loads on it that would be something else, and it is actually a beam. How do we handle that? And so in real practice, then, what this will look like is that if we had the real load, let's say it was the self-weight of the beam and whatever tributary self-weight was coming in there, plus maybe a snowdrift that had built up. And what do you do with that? Because that's not a pure truss. In our model then, what it's going to do is we're going to create equivalent nodal effects. Kind of like in the slope deflection method when we did fixed in moments. We do a similar kind of thing here, of fixed in forces, so to speak, but it's a little easier here because we really do have pin connections everywhere, and so we'll just take whatever the tributary load or the load by equilibrium is, and we'll lump this in as an equivalent model, and now that becomes our F1, F2 values that we're imposing on the system. There's our stiffness coefficients, and then we determine what the displacements are. Once we know those, we feed them back into what does that mean for member elongations. Now we can find member forces. That might seem like a long way to go for a determinate system such as we have for this one, but when you have indeterminate systems, it's quite a bit faster to do it this way.